Okay, hello everybody. Looks like we may have lots of people working on M2 still. Sorry, I should find the remote or the mic here. Let's see. Okay. You guys hear me okay? Yes. All right, I'll try using that mic instead. I can't really find the wireless one. I saw this quote from just a Twitter post. So debugging is like being a detective in a crime movie where you're also the murderer. Thought it was appropriate. So I don't know if any of you have had any trouble debugging M2. If you do, think of that. How's Milestone 2 going? Are the people here the ones who are like in good shape for Milestone 2, or are you the ones who've like given up and you just like tell me about the next milestone? Okay, so I see one person doing a thumbs down, shaking heads. Okay, so are you just trying to scare me, or it really is kind of proving difficult? So okay, maybe talk to me afterwards if you're struggling with it. Hopefully it's not too hard. Remember, you can't do it perfectly. So don't try to get everything that you possibly can think of into it. It's too much work. We're not looking for that. Okay, what we're going to talk about today is milestone 3. And let me quickly ask, can you hear me at the back? Okay, because I'm just using this lecture mic. We'll see how this works. Okay, so milestone 3 is more algorithmic. So there, you'll build on your milestone 2 UI. There's a user interface component to it, but there's also now you're getting into some algorithms. Okay, so what you're gonna do for milestone 3, and you have a little more than 3 weeks for it. So 3 weeks from Friday is when it's due. It's basically 2 pieces. You're trying to find the shortest driving time routes between 2 intersections. It's worth 16% of your final mark. 8% of this is auto-marked. So it's how well does your algorithm work? Can you find a path between the 2 intersections? Get a little bit of marks for that. You get more marks for finding shortest paths. So there are a few tests that just say, did you find any legal path? You found a way to get from St. George and College to Yonge and Bloor. There are more tests that check, is it the shortest path? Did you get the least driving time? And you'll pass those if you get the fastest path. And then you're doing this in a relatively large data structure. You have cities that have a lot of intersections and a lot of streets in them. So we want this to be efficient. So we're also going to test that are some that are kind of medium difficulty and some that are harder difficulty of how fast are you. So depending on how fast your algorithm is, you might pass some of those tests, you might pass all of those tests. So there are public tests so you can see how you're doing. If you don't pass the hardest test, it's not the end of the world. Again, we give part marks for all this. 6% of your mark is your user interface, and your TA will grade that after milestone 3 has been submitted. So he or she will go over it with you. You'll demo it in the lab period afterwards. So that's not auto-marked at all. So it's basically, how do you enter, I want to go from here to there? How do you show the user what the solution is, etc. And then 2% of your mark is code style and project management, just like it was for milestone 2. Okay, it's due in a little more than 3 weeks, 3 weeks from Friday. And we're going to have several lectures on how to attack this. And the underlying algorithms you use for this are actually very fundamental, very important graph algorithms. So they're actually important for all sorts of algorithmic coding. Okay, so you're trying to find a driving path. And we want to find short driving paths, things that get you from A to B quickly. So we need to have an estimate of time. And your estimate of time for a driving path is you take the distance that you go on some street segment, you divide by the speed limit. So we're kind of optimistic. We're assuming traffic is light. You can go the speed limit everywhere. And then there's also a penalty when you turn. So turns usually slow you down. Left turns actually usually slow you down more than right turns, but we're not going to make you differentiate. We're just going to say every time there's a turn, that took a little bit of time. And we'll tell you, there's a variable that will pass into your function called turn penalty. How many seconds of turn time, how many seconds does it take to make a turn? Okay, so let's say we have, we're trying to go from here So Cecil Street and Ross Street to College and McCall. Okay, so the way we compute the travel time, let's say we decide we're going to go down Ross Street, and we're going to go down College Street after that. So we basically take every street segment that we pass through, so this little one, then this longer one, take their length divided by the speed limit, get the travel time, and in milestone 1, you already computed this. Okay, so you already have a function that gives you the travel time to go down any street segment, so you're going to use that. And then we're going to turn at this point, and we're going to go down some more street segments till we get here. Okay? So that's one possible path we could take. And we're going to add a penalty for the turn here. Okay? So we take the travel time of every street segment, and we did one turn. So we're going to add in one turn penalty. That's not the only path. So we could have taken this red path, could have gone right by 100 meters up here, by a couple hundred meters, and so on to the end. And both these paths are the same physical distance. Okay, they're both 500 meters long. Which one of these do you think is actually going to be shorter? If you actually were to drive down this, do these look like they should take the same time, or do you think one of them is going to probably be shorter than the other? I'm going to tell you how you're going to time it, but what do you think? Using your knowledge of driving, do these look like they take about the same time? Assuming there's not much traffic. If there's lots of traffic, then who knows, right? You might have to go on the sidewalk sometimes. So any thoughts? What do you think? Given what I just told you, that we're going to penalize you per turn, which of these do you think is faster? So C07, I'm going to see if I can turn on, oops, I have to go back here and turn on some advanced mode. All right, so let's go to C07 and, okay, you're on the air. Which one?
So the blue one is having one extra turn on the red one, but the red one is having is actual speeding. The actually have one less intersection. So all the seven.
Yeah. So in real life, it might be a bit hard to say. That's true, because there's one more intersection here than there was in this one. The model we're giving you is basically only speed limits and turns count. Okay, so under the model we give you, the blue path would have 200 meters divided by 40 kilometers an hour, because these are slow streets, and 300 meters divided by 50 kilometers an hour, because those are fast streets, and one turn. And we'll say, we'll pass into your function what the turn penalty is. Let's say it's 15 seconds. So this would take about 55 seconds. The other one is a bit slower. We spend longer on small streets that have lower speed limits, and we get two turns. Okay, so both these have speed limits of 40 kilometers an hour instead of the 50 for college. And we get two turns, 15 seconds and 15-second penalty. So it's a bit slow. Okay, so our specification would say that this blue path is better, and that's the one we want you to give us. Okay, so that's what path we want you to return, and we'll talk about algorithms to find that. Let's talk a little bit about the user interface. So the user interface is worth 6% of your mark. There are some requirements, and I'm about to release the actual assignments. You'll see these written down. And you're going to notice that a bunch of these things build on the required features of Milestone 2. So some of them are not that hard because you've already built a lot of what you need. So you should be able to enter two intersections somehow, right? So you enter the names of some streets to find a couple of intersections. So find me the first intersection, find me the second intersection by entering names, and you can find the path between them, okay? You should also be able to click on intersections. So click on two intersections, find the path between them. You want to draw the path in the user interface. So visualize it somehow. And then you want to either print to the terminal or draw on top of your graphics some directions. So how do I get from A to B? And then you should have some way that a person can figure out how to use your interface. So it could be a help button, could be tool tips, You could argue, so something, right? But basically it's, your TA can figure out how to use it without asking you any questions. There's a help button or a little tutorial splash screen or tooltips or something. If you think, look, I've labeled everything so clearly that like you've got to be able to figure it out with no instructions, then fine. But probably better to make a little help button. Okay, so we want this to be usable. And a good way to test usability, usually the team that created things has a blind spot. You know, you created it, you know how the code works, so you try to use it in the way it's intended. If you have somebody else, a friend, a family member, try it, that's a better test of usability because they'll do things that you didn't expect or often be confused by things you didn't expect. So, you know, can he or she enter these intersections that they're trying to go between without a lot of pain? And can he or she follow the directions you give? That they interpret the output path and the travel directions correctly. Okay, so let me give you an example of Dr. Tallman and I have been hard at work on this already. I'm going to give you an example of our travel directions. And I think these are awesome, but Dr. Tallman had some doubts. Okay, so you guys are going to be the deciders. Okay, so we're going to say take street segment number 21, then street segment number 10. Well, I gave a rule away. What do you think? Are these good? So this would be terrible. Okay, so do not give directions that are like this. I'm printing out IDs from the data structures. These are unbelievably bad. Okay, so a bit better would be, let's print the names of each of these street segments. So every street segment knows what street it came from and the street has a name. Okay, so we could say, let's take Young Street, then Young Street, then Bloor Street. Okay, this is my proposal. So, I mean, this was my initial proposal. Dr. Tallman was skeptical, so I've improved it to this new proposal. What do you think of that? So let me clear all of the people on here. It's a bit better. But what do you think about these directions? Is this annoying? Is it good? What do you think? So I'm going to turn you on, and you have to speak loudly.
Although this might be okay for a user to build the brain of street segment, but when user return, it will come by about because it won't know exact section.
Yeah, so these are not very good. Okay, so I'm going to give you a few. Yeah, so it's not good. That would be you're siding with Dr. Tallman. Okay, and I'm not hurt at all. Maybe he's got a point. Okay, so not too easy for someone to follow. Let me take another person. So H08. Do you like him? Do you not like him? Where is H08? This is a test of my eyes.
So overall, I mean, it's better, but I wouldn't actually just say, go right on that tree, go left on that tree.
Yeah, okay, so you flagged an important thing. And it's surprising actually how much when TAs grade this is why it's good to try it on a friend or the things that are missing. So you just said go right or go left. This says take Young Street, then Bloor Street. Think of your following along the directions. You go from Young Street to Bloor Street. It says take it. Which way? Okay, I didn't actually say which way to turn. Okay, so that's bad. I got a 50-50 chance of getting there with these directions. If I had to make 12 turns, or 10 turns, I've got a 1 in 1,000 chance. Sorry, so keep going though. So you flagged an important thing. Not telling people which way to turn is pretty bad. Anything else you don't like about this? Otherwise, you're good? Okay, so you think it's pretty good? Okay, so I see 007. I'm going to go back to them. Or any other ideas? What else do you think?
I don't know if you said this, but if it says take Young Street, then Young Street, people get you don't need to say it twice.
Yeah, this is kind of silly. Yeah, so usually you wouldn't say, I mean, maybe your directions might say stay on Young Street, but only if there's some reason, the street bent or something. We'll see a lot of directions like this. The reason we'll often see them like this is because you're gonna see when you write the algorithm, you're actually following street segments. So you're following city blocks. So if you actually just directly print out your answer, it's actually natural to print out take Young Street, take Young Street, take Young Street, take Young Street. If you take it for like 12 kilometers, you'll actually print out take Young Street 50 times. And it does look quite bizarre. So you don't want to do that. Even though your actual solution is a whole bunch of street segments, so a direct printing out of it would print out just the name of those street segments. So yeah, this isn't all that good. So does this give everything we need to go from the start to the finish? So no, didn't tell us which way to go. It's kind of annoying that it's repeating the street name many times. Let's see. So why don't you take a minute or two, and if you're around people, discuss what do you think you should put in travel directions, and in particular, what you want. We want to see that you give us all the information we need to go from the first intersection to the last one. Nothing missing out, no guesswork, okay? So let's see, I'm gonna set up a timer, take a minute and talk about that. What do you think? Any ideas? I don't think. You can add another minute since it seems like you're still chatting, so it's good. So. Okay, so let's chat about travel direction ideas. Let's see. Anybody want to say what you think a travel direction should have? I heard actually a couple of good ideas from students I went and chatted with, so I'm going to pick on somebody if nobody volunteers. But you can save that, you can avoid that unhappy scenario if you volunteer. Okay, I'm going to try to hear from one other person because we heard from you already, I think, this class. So I'm going to give you another chance. So D13, can I call on you? So we chatted about directions and you had good ideas. Is it okay if I call on you? Probably put you on the spot, so maybe it's a bit awkward anyway, but let me call on you now. Okay, what do you think you should put into these travel directions? Okay. All right. So you said start point, and then you said direction. Is that right? Like east, west, etc. Yeah. And I chatted about this a minute ago. Many teams forget this actually. They won't actually say, they'll say start on Yonge Street, but they won't say whether to go north or south. And if you do that, your TA will notice. We'll actually tell the TAs to watch for that. And you got a 50-50 chance of ever getting to the next spot, right? So you wouldn't be very happy with those directions. So, okay, so you got start point, you got start direction. What would you do next? Right, how far or how long? Okay, so maybe you're saying go on Yonge Street, but don't just say go on Yonge Street, say go on Yonge Street for 1 kilometer or 1 kilometer, about 3 minutes, something like that. Is that right? Okay, so that sounds good. When you say how far, if you say compute street segment length and print that out, you will get something like this. You will get 0.38765. Actually, you won't get 0 point. You'll get it in meters. So you get like 387.6571 meters. You could print that. Do you think you should print that? So yes, do not print, like make them look professional and user-friendly. So your mapping algorithm should not say, go 387.6571 meters on Yonge Street, okay? It also shouldn't say, go 385.7 meters on Yonge Street, and that's one street segment, and then say, now go 200 meters on Yonge Street. Now go 300 more meters on Yonge Street, right? We should combine that together and just talk about Yonge Street. Okay, so I'm with you so far. You said how far to go or how long maybe. And I think you're talking about the name of the street. That's useful to tell the person. What else? Anything else? Yeah, so turn and say left or say right. If you want to be really fancy, you can even say, you know, sometimes there are like sort of slight turns and sharp turns. So you can even be really fancy by saying that. How would you figure this out? How am I going to figure out if I'm turning left or right when I go from one street to the next? So do you have any ideas? I'm going to do first shot. If you don't, I'm going to go to somebody else. Right, yeah, so to find whether you're going left or right, or maybe a little bit left or a lot right, you can take, you know the directions of these street segments, you know the whole path. So you can actually detect, okay, when I leave this street segment, go to the next one, what are the vectors of those two things? And to find the angle between two vectors, you've actually learned how to do that, right? So you can find the angle between two vectors with their cross product. So that's a way that you can go and basically figure out whether you're going left or right and whether you're going a lot left or a lot right and so on. And you can put that into your directions. So yeah, this sounds very good. And then obviously you should end with destination. You know, say when you've arrived so the person doesn't just run out of instructions and like, I don't know what just happened, right? Maybe I'm good, maybe I'm not. So these would be very nice travel directions. But it's actually pretty easy to miss something and make them kind of incomplete or user unfriendly. Okay, so any other thoughts on that? Clear that off. Let's see. We've got a few people in here. I'm going to clear. Let's see. Anyone else? Just put your hand up. I got a bunch of people. Okay, so I'm going to take C07 then and see what you think. Yeah.
So besides the directions we got here, we can also do more for each street, or we can set our challenge.
So it decides the direction. We should also say north on this street.
Yeah, for example, coming towards Wall Street or coming towards Central Wall Street and
Yeah, you can print anything you want. So you could say go north on this street. You could say towards this if you want. That's even more, that'll probably impress your TA, right? As long as you're not just printing random things, like spin around 3 times and point yourself at City Hall. Then yeah, your TA is probably going to be very happy with that. Does that make sense? Okay, H08. I see you were there too, so I'm going to go to you. Yeah.
Yeah, so I think it'd be useful for the guys to kind of indicate on the intersection on which you're driving.
That's a good idea. Yeah, that's a nice idea. If you told the people what the speed limit is on H Street, that's helpful. Okay, and I see one more comment from A09.
Maybe for the intersection between the one and two streets, maybe how to do that exactly and this road that of the land or right. And also maybe also provide
Okay, that sounds good. Yes, these are all good ideas. And obviously you can look at how other people do it. So go look at Google Maps. You don't have to do it the same way as them, but they do tell you, turn left, turn right. They tell you how far to go. That makes sense. Don't miss any of those basic things. And you also are going to draw the path. Okay, so you're going to draw it in the user interface. You could print the directions just to the terminal. So you can print them. You can meet the basic requirements of just printing them out to, send it out. But if you can put them on top of your display or in a dialog box or something, or the status bar at the bottom, it'll look nicer. So there are some marks for kind of aesthetics and usability. You'll get a little bit better on that. But if you want to print them out without too much effort, you can print them to the terminal. Okay, so this milestone is usually one that, usually in this course, milestone 2 and 3 are the ones that students find the most work. Okay, so good news is milestone 4 don't find as much work. But this one tends to be a reasonable amount of work, so start early and make a plan to divide up the work. You don't want to wind up with one person does everything. This milestone, you really don't want to have all 3 people just coding in some kind of triplet programming. One person's coding and the other 2 people are watching. So with what I've described, we've got an algorithm, and we have this user interface where you have to be able to click on intersections. You have to be able to type the names of streets to find intersections. You have to display a path. Any ideas for how you could divide this up? Or do you think it can't be divided up? It's like all so intertwined that one person's got to do it. So what do you think? If you got an idea of how you might divide this up, just hit your microphones. Okay. So I'm going to give a second, see if we can get like a broader participation. So there's somebody we haven't heard from here. This is your chance. Just say how to divide it up. All right. Nobody, but only one person knows how to divide it up. Okay, so you're going to take it away. So.
So maybe one can program this segment admins to another direction, and another person will be able to program the intersection to let it tell which street is connected to the admin to just like one of your function and then
okay, so I'm going to repeat back to you what I think you just said. You said maybe one person can be writing, which street segments are connected to an intersection, and another person can be looking through the intersections. You could do that, but I'd say that is such a fine-grained division of tasks that is challenging. If you divide up tasks where everybody's got just a little bit of work and they have to put together those little bits of work to make the project come together, it's challenging to be efficient. So if you can find kind of larger tasks that are less coupled, you get more parallel development. You're not in each other's way as much. So can you think of any larger tasks that you could divide up where, yeah, people can be out of each other's way more? Okay. I'm going to give you a moment to think about it. So, okay, I see it's up at the back. Let's see, press it hard. I actually don't see it alive yet. Huh, that's interesting. Okay, so what number are you? I'll try turning your mic on. 808. Okay, I think you're on anyway, so go for it.
I was thinking maybe divide up into like a UI part and a part. So something handles the more visual graphic aspects, and then somebody else handles the so like the more happy side.
Yeah, and I would say that makes a lot of sense. So divide up the UI from the algorithm, and then we can further subdivide those because that's only two pieces, and you got three people, so hopefully we can divide it more than that. But that's a very nice dividing line. Those things are not highly coupled. So yeah, let's divide UI and algorithm. Now here's something that often happens. We have unit tests for the algorithm. Okay, so you're going to see this when I release the milestone document. But basically, we can call your algorithm by just passing you two intersections and saying return a path between them. So it's pretty obvious how the person who's writing the algorithm doesn't really need to wait for the UI because it can be called by the unit tests. The UI should actually call the algorithm the exact same way. Just pass those two intersections and ask for a path to come back. But what about the people writing the UI? How can they write the UI when the algorithm's not done yet? What do you think? Yeah.
Maybe sort of make a container that you can fill in the algorithm later. So just implement the feature that you can and then stuff it, stuff the algorithm part and then just fill in the algorithm.
Yeah, so it makes sense. You can use the stubbing out technique again. So there's one piece of the UI which is like input to the algorithm. Okay, find me two intersections, either by clicking on them or by entering the names of streets and they define two intersections. Okay, that can clearly be done before the algorithm's done because that would provide input to the algorithm. So that's one piece that can be done. The algorithm is also separate because you can just test it with the unit tests. Doesn't really need to wait for input from the UI. And then there's this final piece of displaying the path. And you might think, well, I can't display the path till the algorithm's done because I don't have a path. But you can essentially stub it out, as was just suggested. Just hard code one path. Just so the way that we're going to store a path is going to be in a vector. You can just make one path by hand, stick it in a vector, put it in your code, and the person who's displaying paths can just use that as their test case. And it doesn't matter if the algorithm doesn't exist yet. They're just going to visualize that one path and make sure it works. Does that make sense? So you want to break barriers that stop parallel development like that. Okay, so I'm just going to add a few notes like this, which basically you just captured. So the UI input is one separate task. And in fact, you can separate the text and the mouse input. The UI output is another task. So drawing what the path is, giving directions. And again, so that you don't have to wait for the algorithm to work, just hard code a test path or hard code a couple of test paths. The algorithm itself is pretty big, okay? So the algorithm might take a while. So it might be, this is a natural division. You could have one person writing the input UI, another person writing the output UI, and a third person writing the algorithm. But there is some risk now that the algorithm might not get done or have time for tuning. So if you do this, make sure that these two tasks get done relatively early. And there's time for people to help the algorithm developer. How can you have more than one person working on an algorithm? You could have one person get a basic algorithm working. You could have other people helping by testing. And testing and maybe tuning, so trying new ideas. And you may be able to define some helper functions. Okay, I need a function that does this for me. Now that needs closer communication, where you have to spec out, I need you to do exactly that. That's kind of the idea that was suggested at the start. So you can do that, but it needs more communication. Okay, but definitely you want to get going on this with all three people doing things. Okay, so that's all I'm going to talk about for the user interface. So let's talk about the algorithms. So we're trying to find paths in a graph. So how do we do that? So we already talked about this in the first couple of lectures. We're going to model a city as a graph. Okay, so we have intersections, which are nodes, and we have street segments, which are edges. And what we're trying to find, we're given a source intersection and a destination intersection, and we're trying to find a path between them. So a path is a sequence of connected nodes that go all the way from the source to the destination. Okay, so this could be my path, like all those arrows. Okay, so how should we store that path? So I could store the sequence of nodes. This node has a certain ID, this node has an ID, et cetera, et cetera. I could stick all those IDs of the nodes into a vector, and that could be my path. Okay? So what do you think? That's one way that I can encode this. It's not unreasonable. So that would be a reasonable way to encode a path. There is a case where it's kind of a bit flawed, though. So this is not the way we're going to have you encode the result. Why? What is the case where this is a bit flawed? And what I mean by flawed is where it doesn't actually fully tell you what you need, does not fully describe the travel route. So I think C07, you have an idea? Or actually B07, looks like you might have an idea. Let's go to you. So not bad, but not perfect. It is possible. You could actually have a cul-de-sac. Okay, so that can occur. So you could have that. And I think you're on to the right idea, which is basically, what if there are multiple options in terms of edges that we could follow? So one would be this cul-de-sac. Are we supposed to follow it or not? And you might say, well, don't follow cul-de-sacs. They never get you there. But another case could be, maybe I got a back lane, or just two different roads that go between two different intersections. That does happen with things like back lanes. So now the sequence of nodes doesn't uniquely define the path. There's still a little bit of ambiguity in some cases. So we're not going to use that as our path format. What we're going to do is we're going to actually use the edges. So, and edges in our graph are basically the street segments. So if we're given a vector that has the sequence of street segments to follow in order, that is enough to uniquely define a path. And it's even enough if we have these back lanes and all sorts of complicated things in our graph. And those edges imply the intersections as well. We can look at the start and end of them, and that's fine. Let me see if I don't know if that's B or someone else, okay? You think it's the, okay, it's back up there? Okay. Okay, so that's how we're going to encode the solution. How are we going to find this? Well, let me ask you another question. Oops, is it? Oh, okay, sorry. Got it, thanks. That was, thank you for the catch. Okay. When we go from the source to the destination, is there only one path? So from this source to this destination, is there one path, or are there many possible paths we could follow? So what do you think? You got an idea, just tell. What do you think? So we're going to stop you there. So your answer is many. This is like a yes, there are many, or no, there's one. What do you think? Yeah, so there's many paths. Okay, so finding any path is not really good enough. We want you to, I mean, it'll be good for a few marks. You'll pass a few test cases, but we want you to find good paths. Okay. So what is a good path? So a good path could be the fewest nodes. So go through the fewest intersections, or fewest street segments. So go through the fewest city blocks. What do you think the best path would be for travel directions? How would you define it? So what do you think? For this problem, what do you think the best path should be? What one do we want you to return? And there might be a few that are close to ties. We'll accept all of those. That's fine. But how should you decide which path is a good one? Okay, so any path is not very good. Don't do that. Fewest nodes. Okay, so you're trying to go through the fewest intersections. Is that the most important thing for somebody driving? Probably not. So what do they care about? So what do you think? C04, what do you care about when you're driving? Yeah, time and distance. And we're going to go with time, okay? Which correlates with distance, but with speed limits and so on, it might not be the same. So what we want is minimum travel time, okay? In graph texts, so if you go to the algorithms textbook that I referred you to a few lectures ago, this is defined as, it's a classic graph problem. It's actually an important algorithm, and it's a building block in lots of other algorithms. It's called the shortest path algorithm or the minimum weight path. Okay, so our weight is based on every edge. We have a weight. That weight is travel time. Okay, we actually have changed it a bit by putting also a turn penalty. So there's a little bit of an extra term in the cost function, and we're trying to find shortest path under that function. Okay, so this is our definition of travel time. Take the street segment length divided by its speed limit, add that up, and take all the turn penalties. When do you have a turn? So we're going to keep it pretty simple of when you have a turn. If you change street IDs, you have a turn. Okay, so when you go from Yonge Street to Bloor Street, you have a penalty. And in our case, even going from Bloor Street West to Bloor Street East, those actually have different street IDs, so we're going to call that a turn penalty too. Okay, so you don't have to do a bunch of vector calculations to figure out is this a turn or not. We're just going to say if the street ID changes, it's a turn. But in this case, there is no turn, but there's probably a traffic light there, so it's fine anyway. So you can think of it as changing street penalty, and that's how you should code it. Okay, but if I stay on the same street, so if I go through this intersection this way, I'm on one street segment, then a different street segment, but they both have the same street ID, so I don't take this penalty. But all the other cases going through here, I would. Sound good? Okay, so that's the specification. We're using this shortest path in a street problem, a logistics problem, which they are used for a lot. Can you think of any other applications where you might use shortest path algorithms? Because there are actually a lot of them. So you just change the graph and you can run this algorithm and it solves a different problem. Can you think of any other cases where we might use shortest path algorithms? In society, engineering, whatever you want. See if anybody can think of any. Okay, so I'm going to go to B07. Actually, C07, you're in first. Why don't you go for it?
Is it possible to be used when you're designing circuits to be like a decent amount of water?
Yeah. So that's exactly right. You actually use algorithms like this to lay out the wires in computer chips. So that's one of them. Any other ideas? Okay, so I see H08. Let's go to you. Let me unmute you.
So don't we use track block to find shortest path between like two friends, for example, on Facebook?
Yeah. So you can use shortest path algorithms to find friends, and those actually are building blocks for algorithms that do things like social marketing. There's actually a whole research area about if you've got an ad campaign budget and you're going to pay a bunch of influencers, who do you pay? And they actually use shortest path algorithms within social network graphs to try to figure out who has the most influence. So yeah, it's also a good idea. Let's see, B07, you already had your idea taken or not? I'm going to turn you, okay, so I got your mic on now, I think. Sorry, I had trouble hearing that through all the feedback. So let me try it one more time.
It was like, you can make kind of users based on the way of your stack.
Okay, so use it for scheduling things like assignments and so on? Yeah, so you can use it as, so let me clear all that. Yeah, you can use it as a building block for algorithms that do things like schedule tasks. So that's true too. Okay, so I'm going to go on to show you a few of these. So one is internet routing. So when you send packets from your computer to another computer, the way the internet knows where to send them is it actually uses shortest path algorithms to figure out what are all the intermediate hops that I should use. And in that case, nodes are computers and switches, your edges are cables, and you try to find a path through this graph to connect the computers. And that path is, you can define what is the best path, what's the minimum weight or shortest path in a few ways. So it could be the fewest routers. Okay, so here I go through 3 routers. But you could also have essentially different weights or costs for each router based on congestion. So some router is overloaded, you try to avoid it. And shortest path algorithms do that automatically if you give them the right cost function. Circuit board design. Okay, so you take a printed circuit board, it's got multiple levels of metal with dielectrics in between, and you can connect, so you can draw basically circuit traces, pieces of wire, and you can connect different layers. Like these can't cross or they short out, but you can connect them with what are called vias. That's shown here. Okay, so you can basically drill holes through the board, fill that with copper, and now you can go between layers for some connections. You can model that problem as a graph. You divide up the circuit board into little pieces, and every piece becomes a node. And for different layers, you have different nodes, and you have edges between pieces that are right beside each other or right above each other. And once you've done your shortest path algorithm, you basically say all those pieces get filled with copper. Okay, you do that for a whole bunch of like connections from components, and you wind up with a circuit board. Integrated circuits. So you use the same kinds of algorithms inside integrated circuits where you're designing a whole chip. They're just much bigger. So circuit boards, their complexity is thousands of signals on a really complicated circuit board. Usually it's hundreds. Really complicated board might be thousands. On a modern computer chip, it is billions. Okay, so the scale is much bigger of how many connections you have to make. But the idea is the same. You have layers of metal, and you can choose on different grid spots, do I put metal or not? And you can go between those layers. Typical computer chips now have like 10, 11 layers of metal. You can go between them with vias that are basically holes in the dielectrics that are filled with copper. Same basic algorithm, right? You model the geometry as a graph, do searches for paths connecting circuit components through that graph, but you have literally, you may have a billion connections to make in a graph that has hundreds of billions of nodes. So the scale of it is very large. So you need really fast algorithms for that. Facebook, so this was mentioned, social networks. Facebook models its key data is actually one giant graph. So they have a graph with over 1 billion nodes. Each node is a person. And they store it as one entire graph so they can do graph searches to find friends. And some of the more, so shortest path is how close are you to knowing someone? And I already mentioned this, but basically social marketing is actually an interesting research field, like from a technical point of view, from a societal value point of view, I'm less sure. But they build algorithms on top of these shortest path, find who's connected to who and how closely they're connected, to work out how do we do social marketing campaigns. So which Kardashian should we bring on board and so on in order to have the most influence in the least time. Okay, so shortest path is important. Next week, we're going to start talking about algorithmic approaches. So we'll start off with the simple one, and then we're going to gradually build up to faster and faster algorithmic approaches. Because as you can see, the scale of these problems can be very big, very large graphs. So it's important to be able to solve them efficiently and quickly. Okay, and that's all I have for today. I'll be down here in case you have any questions about Milestone 2 or anything else. Thanks, everybody.